So I'm Kieran Iles. I work with PFC Ross at INRS, and I'm going to give an overview of the geochemistry of the Deloro Assemblage from the Abitibi and make some connections between these volcanic rock compositions and the VMS deposits. So we're located here in the Abitibi, where the volcanic rocks are divided into 7 assemblages, from the pre-2750 to the Blake River, which is 2704, 2695. And amongst these, you have sedimentary assemblages that cap the volcanics and intrusives that range from synvolcanic to post-Temiskaming in age. The reason why we're interested is VMS. It's kind of obvious by now. The Superior Province hosts a large tonnage of VMS, and many of these are in Abitibi. But if we look at, for example, the Deloro Assemblage, which is the second largest by area and has the largest number of VMS deposits, you can see the this wedge here of the pie chart is the largest, and it's also a very significant assemblage in terms of endowment. And this is quite in contrast with, you look at another assemblage like Stone Rockmore, which is even larger as an assemblage, but is nearly barren. So there are these contrasts, and we're quite interested in why VMS endowment is variable at different scales. In particular, what I'm looking at is the differences within and between assemblages in terms of geochemistry and petrogenesis. So, the Deloro assemblage is the 2734 to 2724 assemblage of mafic to felsic calc-alkaline and tholeitic affinity rocks. There are a large number of VMS deposits. There are also some other deposit types. And we're working with a data set of around 1,200 samples that were extracted from our larger, 2,400 samples extracted from our larger 12,000 Abitibi-wide data set. And in some of the plots that I will show, there's magnesium, and whenever a major element is plotted on throughout the talk, this comes from this least altered subset of 1,300 samples. So before I can continue and get into VMS eventually, this connection, I'm going to give an overview of what I presented at the Ottawa meeting last year. So I'm not going to give all the details of geochemistry and modelling, but a snapshot of that, because it sets up a framework for how we talk about connections between volcanic rocks and VMS. So the geochemistry, we did principal component analysis, K-means clustering on the database, and looked at various ratio plots to understand geochemical groups within the dataset. And this can be represented on this thorium-ytterbium versus ytterbium-titanium plot. And I identified 9 geochemical groups in Deloro: the tholeitic basalts, high thorium basalts, calc-alkaline andesites, heavy rare earth depleted intermediate group, the transitional intermediate, the tholeitic dacites and rhyolites, and the calc-alkaline dacites and calc-alkaline rhyolites. So each of these groups have coherent patterns within them, and neighbouring groups will show some similarities, but there are distinct geochemical characteristics that can be used to distinguish the groups from each other. And I'll now give you an overview of what these characteristics are. We'll return to our thorium-ytterbium versus ytterbium-titanium plot showing the groups. In the upper panel are the group averages for mafic to intermediate groups, and the lower are the averages for the felsic groups. Starting with the tholeitic basalts, this blue line, you get a very flat trace element pattern. This is primitive mantle normalized. As we look amongst these groups, you see the development of strong enrichment of thorium and light rare earths, a depletion of the heavy rare earths, and the development of niobium, titanium, and europium anomalies. One group in particular, this group in purple, has an even stronger heavy rare earth depletion. That's why it has its name. It's quite distinctive in comparison to the others. We move down into the felsic groups, we see an overall enrichment in most trace elements compared to their mafic to intermediate counterparts, but an even stronger development of europium and titanium anomalies. Okay. The characteristics of the geochemical groups were explored using geochemical modelling, primarily using the magma chamber simulator. So we can start out by thinking about a magma that undergoes fractional crystallization, sitting in some sort of magma body, don't get too distracted by the shape. And this gives us our fractional crystallization only models, and you'll see some of those shortly. We can also think of this magma body being coupled to a wall rock, which, because of the heat of the magma body, undergoes partial melting, and that melt can contribute to the magma and cause a different evolution, creating these AFC trends. Another alternative is to have the magma body periodically replenished by more primitive magma throughout the crystallization. These are the recharge or RFC models. And slightly stepping outside of the MCS realm, I also looked at mixing directly between a tholeiitic basaltic magma and a TTG composition. In order to do the MCS models, we start with a parental magma, and in this case, it represents the most mafic Deloro samples. Some variation in that composition comes from testing a bit of variation in the water, but in terms of trace elements, we have this flat trace element pattern, the white line, which is quite similar to the average tholeite. In any recharge model, that tholeiitic parental magma is used as the recharge, so it's fluxed with that same primitive magma periodically. In the AFC models, the wall rock is an average Southeast Superior Province TTG, and this is shown by the red line. It has a lot of characteristics of these two other groups, particularly that depletion. And the conditions of the models are partly established by previous Abitibi modelling. So we have an idea of the pressure and oxygen fugacity that's suitable and that makes sense for the major element compositions. And for trace element modelling, we need to constrain partition coefficients, which I did by looking at a variety of literature studies. Okay, I'm now going to jump into kind of the summary of the modelling, the real conclusions of it, and look at primarily trace element ratios. So we start on the left with ytterbium titanium versus magnesium oxide to show that ytterbium titanium increases with fractionation, so it sort of tracks that aspect of a system, particularly as you move from the intermediate through to the felsic part of the data. Additionally, we have in orange 2 examples of fractional crystallization only models that explain a certain portion of this data, but with the recharge FC models, we're able to explain another part of the Abitibi data set. So they both probably have a role to play. You can see there's an assimilation model in there too. If we look at the right and have thorium ytterbium versus ytterbium titanium, we can see that thorium ytterbium really tracks a contamination process. Looking here at this jump, there's a really large step. As soon as you have a little bit of wall rock partial melt assimilated into the magma, the AFC trend increases in thorium ytterbium a lot. This is because the first bit of partial melt from a wall rock will be really rich in thorium particularly and have a high thorium ytterbium ratio. What this plot also highlights is a difference between 2 different contamination paths. The AFC path that goes off to the right and towards higher ytterbium titanium, and the direct mixing pathway which stays at the low ytterbium but high thorium ytterbium values. You can also see this cluster of data points around the TTG average at the end of the mixing line that suggests that some of these volcanic rocks are equivalent of the TTG magmas that make this average. In order to synthesize these different models and integrate them with the different geochemical groups identified, I'm going to walk through 3 basic pathways that models give us to explain the different geochemical groups. And I'll start with the RFC model. It goes this way. With increasing amount of fractional crystallization, you can move from tholodic basalts to transitional intermediate to tholodic dacites. And as we go to further and further fractional crystallization and get to really the later stages and low melt compositions, we reach the tholodic rhyolite compositions. The next alternative pathway is the AFC one, where with about 50% crystallization and a very small amount of assimilation, we already get to high thorium basalts. As we assimilate more and continue this process, we explain the calc-alkaline andesites and calc-alkaline dacites, and then fractionation pushes us further over through the dacites and into the calc-alkaline rhyolites. And the final pathway is the mixing pathway, where as we increase the proportions of the T2G end member relative to the tholodic end member, we go through these high thorium basalts and calc-alkaline andesites. And then once you're at the composition of the heavy rare earth depleted intermediate group, it is dominated by the T2G signature. Okay, so that is our geochemical and petrogenetic framework, and I'm now going to look at the connection between VMS and the chemistry of the volcanic rocks. The idea here is to identify what geochemical characteristics are in the volcanic rock samples that are most directly associated with where the VMS are found. And so to do this, we look at where the VMS are. On this map, which is a section of Matagami, you see these blue blobs. These are the VMS deposits mapped. And what we want to do is look at the immediate footwall, about 1,000 meters into the footwall, to see what volcanic rocks were being produced just before the VMS were being made, and 500 meters into the hanging wall, so that's just after and contemporaneous with the VMS deposits. So knowing where the deposits are on the map, I've marked out this mineralized horizon you see, and then we can say, okay, this, accounting for what the dip is, this is the zone on the map where that's 1,000 meters into the footwall. And then look at where the upper limits of the deposits are and map out this other area. So that goes up into the hanging wall. So everywhere in this blue is what we have taken as our volcanic rocks associated very closely with VMS, and that's the sample set we're calling the mineralized samples. So for each area, I would then take all those samples and calculate the proportions of the different geochemical groups for comparison, and we can calculate an average Deloro mineralized by weighting these different areas according to the tonnage. Doing this, we get the Deloro as a whole has different proportions of geochemical groups, and then this all Deloro mineralized has a different set of proportions. I've just marked off what of those geochemical groups are felsic, and you can see that whereas the Deloro as a whole is dominated by mafic to intermediate groups, you see a large amount of tholodic basalts and calc-alkaline andesites, the mineralized units are dominated by felsic geochemical groups. This is probably not super surprising, but that's what we have. Another way of looking at it is to plot each group on a radial diagram. So each group has an axis. The blue line represents the Deloro as a whole, and the orange line the mineralized samples. So here you can really see quite obviously the tholodic basalts, high thorium basalts, and calc-alkaline andesites stand out as dominating Deloro geochemistry. And in contrast, in the mineralized, the tholodic basalts are really much less important. And we can also start to see which of these groups are really the key players in terms of where the VMS are found. So our high achievers, the tholeidic dacites, tholeidic rhyolites and calcalcline andesites here are really hitting above their weight in comparison to their proportions in Deloro as a whole. We might give honourable mention to the calcalcline andesites that are a high proportion amongst mineralised samples, but they're underperforming relative to what their proportion is in the whole assemblage. The calcalcline dacites are like overperforming relative to Deloro as a whole, but they're not as important for mineralised as these other three groups. And then we also see the infertile group. This heavy rare earth depleted intermediate group has basically no mineralisation associated. I'm going to look at two areas for a bit of a closer study and analysis, Matagami and Selbaie. Starting with Matagami, we have this map on the right. This is the lithological map from Sijom. The samples are shown colour-coded according to their geochemical group, and the orange stars mark out the VMS deposits in the west camp, the south flank, and over in the north flank. So there's significant VMS deposits, 69 megatons approximately. And if I look at what we would call the mineralised samples, just remove a bunch of the data points, they're around here, here, and across here. You see a lot of tholeidic dacites and rhyolites of the Watson Lake group, as well as some of those and some transitional intermediate and high thorium basalts at the base of the Riviere Allard, which is the hanging wall units of the VMS deposits. And if I bring back the whole data set for Matagami area, you see other areas where the tholeidic basalts, high thorium basalts, and calcalcline andesites dominate these much younger units that are further from where the deposits are formed. Okay, let's move forward. In the Selbaie area, there's a lot, you can't see as much of the data points because a lot of these come from drill holes, so they're kind of plotting on top of each other, but we have two deposits. Selbaie is very well endowed, about similar to the total tonnage as Matagami really, but it's a contrasting example. Here there are high thorium basalts, calcalcline andesites, calcalcline dacites and rhyolites. And we can compare this again on a bar chart where we again have Deloro as a whole, mineralised, and then Matagami alone, Selbaie alone, and these are the mineralised Matagami and mineralised Selbaie. And these represent two contrasting systems in terms of Deloro. Matagami is tholeidic to transitional in affinity, very little contaminated signature, whereas Selbaie is dominated by a contaminated signature and as a distinct calcalcline affinity. We can break out the felsic, intermediate, and mafic groups, and you see there's another contrast. Matagami has mostly felsic and an important contribution from mafic, but very little intermediate, whereas Selbaie is dominated by felsic, has an important component of calcalcline andesites, that's an intermediate composition, and very small contribution from mafic samples. Looking at this a little bit closer, we can pull up the mineralised samples on our thorium ytterbium versus ytterbium titanium plot to link it to the models and what we know about processes that cause the compositions. And you see that these mineralised Matagami samples, which are the blue dots, compared to the grey is just all of Deloro, that in Matagami, extreme fractionation is really needed to get to the Watson Lake rhyolites, which are around here, and the fractional crystallization and RFC models explain a lot of this variation here. There is a small component up that mixing trend, but there's not a lot of the samples going in that direction. Now we can look at the right and similarly plot the Selbaie Matagami. So now we've got that blue is Selbaie mineralized samples and Deloro in the background. In this case, we now need a lot of contamination. There's a cluster of Selbaie around halfway up the mixing trend, and you also have a lot of them along the AFC trend and an important contribution at the calcalcline rhyolite compositions here. What is common between these two is that both systems have extensive low-pressure fractional crystallization. And this suggests a large upper crustal magma system. This would have a high heat flow, which could be favourable for VMS formation. To summarise these, we have the Deloro Assemblage is geochemically diverse. There are 9 geochemical groups. And in terms of petrogenesis, you need an interplay of fractional crystallisation, recharge, mixing, and assimilation. The VMS deposits aren't associated with any particular geochemical group, but they are associated with extensive fractionation and differentiation in a shallow magma chamber. And these seem to be associated with long-lived systems where there's a lot of magmatic processing going on to get the system that makes a VMS. The next stages that I'll be working on are looking more closely at the felsic compositions and doing further modelling, so looking at the role of zircon in fractional crystallisation models and modelling partial melting to see if there are ways to create these rhyolitic compositions from partial melting, whereas we show you can get them from fractional crystallisation. That's definitely a viable way to go. And the other component is a larger scale, the comparison of the geochemistry of the different Abitibi assemblages. Okay, thank you.